So here is the outline for the supplementary notes for the Maxwell equation. So we will actually introduce the differential form of the Maxwell equation. Actually, in the lecture in chapter 23, 28, 29, 29 and 30, we learned the Gauss Law, the Ampere's Law, and also the Faraday's Law. And also in chapter 32, we also talk about the Gauss Law for the B field. Actually, in the textbook, it only mentioned the integration form or the integral form. And actually, when as much as the Maxwell equation is useful for its differential form, especially when you need to use a computer to solve some structures. So actually, I will introduce the differential form. How can we derive the differential form from the integral form with some multi-variable calculus? And in between, I will also introduce the Divergence Theorem, which is also known as the Gauss Theorem. So when you see the name Gauss Theorem, you can imagine it is related to the Gauss Law. And also, we'll talk about the Stock Theorem. The Stock Theorem related to the Ampere's Law and also the Faraday's Law. And finally, I would also talk about the conservation of charge, which is related to the displacement current. Because when we learn the displacement current, you feel like, oh, we first have the Ampere's Law without the displacement current, and then we try to add something to it. But you may have a question whether we need to add other terms to it. But here it tells you that we don't need that. In order to satisfy the conservation of charge or conservation of charge, the current and also the displacement current is sufficient, and no more things is necessary. Okay, so here is the summary of the Maxwell equation, so which is called the integral form. So we have the Gauss Law, and then this is the Gauss Law for magnetism. This is the Faraday's Law. This is the Ampere's Law. So this is nothing special. I just write it as what we have learned before. And actually, I only call it Ampere's Law rather than Ampere-Maxwell's Law, although the textbook it call the whole thing the Ampere-Maxwell's Law, but I used to call it Ampere's Law only. Okay, so we try to make some modification to it. So for the Faraday's Law, originally on the right side we have a d phi b dt, which is the derivative of the magnetic flux, and then with respect to time, and then take the minus sign. So here for this phi b, we try to rewrite it as the surface integral. The phi b is actually the surface integral b dot dA, like this. And also for this one, originally this is d phi e dt, which is the derivative of the electric flux with respect to time for this term. So we also write phi e as an integration of e dot dA. So to make this four equation consists only of e, b, e, b, e, b, and also I enclosed and q enclosed. Other things are constant. E0 is constant. Epsilon 0, mu 0 are constant. So to make things only consist of E field, B field, and also Q enclosed, I enclosed, and also mu naught, epsilon naught. So within this one, we only consist of these 6. So these are two field, and then these two are considered as the sources, and then the constant. Okay, So furthermore, we try to rewrite this Q enclosed into a triple integral, So this triple integral is, I think it is easy to understand because this Q enclosed means the total charge enclosed by the Gaussian surface, the total charge, and the rho here is the charge density. So the charge density. So if the charge density is uniform, the total charge is nothing but the charge density multiplied by the volume. But here, we consider the charge density might not be uniform. So we try to use a triple integral. We use a triple integral to stand for this whole total charge amount. And yeah, actually different from the textbook. The textbook only use a single integral sign to stand for everything. Even for surface integral, it use a single integral sign. And then for line integral, it also use a single integral sign. But in some of the mathematics textbook, it would generally use two integral signs for the surface integral and one for the line integral and three integral signs for the three-dimensional integral. So this is just a notation, which is nothing special. We didn't really dive in deep on how to calculate this stuff, but it's just a physical meaning. It's just a physical meaning or physical notation to represent the integral for the volume, integral for the surface, integral for the line. So with 1, 2, and 3 integral sign respectively. And of course for closed integral, we still use a circle there to represent, this is the surface integral for the closed surface. This is the integral for the closed loop or the ambient loop. And here, this is open. Maybe this is, I think maybe this is closed. We actually need the circle there to stand for this surface. Or maybe we don't really need this one because just integrate for the specific region. Okay, so and for this one, this is not as a closed surface, so we don't have a circle here. And also for this one, this is I enclosed. We write it as a double integral of the current density. So the density multiplied by the area and then take the double integral. So we try to make things look so complicated, but actually it is not so difficult to understand, I think. Okay, so this is the preparation stuff before we try to get the differential form. So up till now, any questions? Okay, so actually this is the differential form of the Maxwell equation. So it's simply, I think it generally looks easier because we have less thing to write, but there are some horrible stuff like this upside down triangle, and then with this dot, with this cross. Of course, this is a cross product, this is a dot product. And actually, this upside down triangle, I think you have learned it before in chapter 24 when we talk about the electric potential. We have an equation like E equals negative gradient V. We have actually seen this upside down triangle before, and here this is a little bit different. This is a gradient with a dot, and we call this one the divergence. And then later we have a divergence theorem, as I mentioned before. So this is the divergence. This is called the curl. This is called the curl. And then for the Gauss law, the two Gauss law, we have divergence on the left side. So this is a divergence of the E field equals the current density over the epsilon naught, over the constant. And then for the Gauss law of magnetism, we have a divergence of the B field equals 0. So this is very neat. Okay. And then for the Faraday's law, we have a curl of E field equals the negative partial derivative of the B field with respect to time. This is the Faraday's law. And for the Ampere's law, the curl of the B field equals mu naught multiplied by the current density plus epsilon naught times the partial derivative of the E field with respect to time. So you can try to understand why we need to rewrite this Q into the triple integration of this charge density, and also we need to rewrite this current into the double integration of the current density. So yeah, so this is this term and this term really appear in here and here. Okay, and then we can try to see how we can come up with this differential form of the Maxwell equations. So yeah, so this is a summary. So the left side is the integral form for the Gauss law, and then Faraday's law and Ampere's law. So it looks like this. Looks so quite complicated, and this is the differential form. So you can see here E dot dA becomes E dot divergence of E, and then this surface integration becomes divergence of B, and then for the right side, this one diminished, only have a rho over epsilon naught on the right side. Here we have 0 on the right side. And then for the Faraday's law, we have this line integral, this line integral. So these two line integral become the curl of this E field and B field. And on the right side, we have this one. This is the surface integral. Take the partial derivative. So it just like cancel these two, this integration. So it remains a partial B, partial T. Actually, we need to use a partial derivative here rather than the original differential. Because for this case, B dot dA becomes a scalar. So yeah, and here we can just take the original derivative, but here B is a function of x, y, z, and t. So we need to take the partial derivative. Okay, so here this term is similar to this term, so you can also imagine this term becomes partial B, partial t, and this term becomes partial E, partial t, like this. And then here we also cancel this integration sign, so we only have J here. Okay, so this is a comparison between the integration form and differential form. Okay, so here we talk about what is the divergence. So in chapter 24, we already know what is a gradient operator. And of course, this one is defined in the Cartesian coordinate. So this gradient is nothing but a partial x times the unit vector in x direction, and then plus a partial y times the unit vector in y direction, and plus a partial z times the unit vector in z direction. Okay, so this is the gradient operator. It can operate to something else, or actually operate on a scalar field, operate on something, and this is a scalar field. Scalar field. Okay, scalar field. Okay, so here, with this one, we can define the divergence. The divergence. So the divergence is the gradient with an inner product. It can operate on something else. And actually, it can operate on a vector field. And as I mentioned in the previous slide, we will add this one on the E field or the B field, or of course any other vector field. But yeah, E field and B field are two of the possible vector field. Okay, so this is the divergence. This is the divergence. Okay. Vector field. Okay. So here, yeah, we also make this one in the Cartesian coordinate. If it is in other coordinate like cylindrical coordinate or spherical coordinate, the expression will be different. But of course, I don't try to go too deep here, so I just explain the simplest case as the Cartesian coordinate. Okay, so suppose we need to add this divergence operator on a vector field called F. So this F vector also in Cartesian coordinate can be written as f of fx times I hat plus fy times j hat plus fz times k hat. So we represent this vector field in Cartesian coordinate with fx, fy, fz as the different components. So yeah, so actually the divergence is like we try to add this one on here, which is like this one is partial x and then I hat plus partial y j hat plus partial z k hat, and then inner product, this dot is the inner product, and then fx and then times I hat plus fy times j hat plus fz k hat, like this. Okay, so you can distribute this one to here, to here, to here, which means that we have I hat dot I hat, which will be 1, and then I hat dot j hat will be 0, I hat dot k hat will be 0. So for the first term, we only have a partial x fx, which is this term. Partial x with this term, because I hat is 1, but I hat dot other hat will be 0. And similarly, for partial y j hat, we distribute to 1, 2, 3, but j hat dot I hat will be 0, j hat dot j hat will be 1, j hat dot k hat will be 0. Okay, so the only remaining term is partial fy partial y, which is this one. And then similarly, for the third term, we distribute, and then k hat dot I hat is 0, k hat dot j hat is 0, k hat dot k is 1. So the remaining one is partial fz partial z, which is this one. Okay, so this is the divergence operator in the Cartesian coordinate. So which means that if we have a vector field, we take the component with different axes and then take the partial derivative in that direction, and then we add them together. So this one becomes a scalar field, and the result becomes a scalar field. Okay, we originally have a vector field, and then we have this divergence act on it, it becomes a scalar field because we don't have any vector in here anymore. This is a component taking the derivative is still a scalar field, and then we add them together. Okay, so what does it mean? It looks so complicated. Okay, so here is the physical interpretation. So if divergence of f is larger than 0 at a point, which means that the f is flowing outward. If the divergence of f is smaller than 0 at the point, then the f is flowing inside, flowing into that point. If divergence of f is 0, then it feels like the f vector flowing in, flowing out at the point is totally 0. It's totally 0. Okay, so it's somehow similar to when we consider the Gauss Law, which is like integration of E dot dA. If it is larger than 0, then this is that case when we consider the Gaussian surface, and then the electric flux is flowing outward. And if it is 0, there is no net flux. And then if it is smaller than 0, the net flux is going into the region. Okay, so it can correspond to these three situations. Okay, so this is the divergence. Okay, and then the other one is the curl. So the curl looks a bit more complicated. Okay, so this is curl. Of course, this is still in Cartesian coordinate. And then here we try to add this curl on a vector field, still call it f. And then, of course, this is a cross product. And yeah, so we try to use the previous definition. So this is the gradient. So this is the gradient in Cartesian coordinate, and then the cross product. And then this is the vector field f. We put it here. So we have a cross product of this one and this one. Of course, one way to calculate is to use this determinant. Yeah, for determinant of 3 times 3, it is possible to for hand calculation, which is like you try to have this one, and this one. So I had partial y and fc with a positive sign. So we have I partial y fc, which is this one. Partial fc partial y I with a positive sign, which is this is the first one. Okay. So and the second one is this one. J hat partial z and then fx, also with a positive sign. And then you can check it partial c fx, partial c fx. Oh, this one. This is the second one. This is the first one. This is the second one. You can see j hat partial z and then fx. And then the final one, k hat partial x plus fy. This is the third one with the positive sign. So you can see it here. So you can see k hat and then partial x fy, partial x fy. Okay, so this is the 3 terms with a positive sign. And also you can find another 3 terms. This one, I partial c partial z fy with negative sign, negative the first one. So you can see it here. Yeah. I had and then partial z and then fy here, and then with a negative sign. So if it is diagonal this way, from top right to bottom left, it will have a negative sign. If it is diagonal line from top left to bottom right, it will have a positive sign. Okay, so for the second one, j hat partial x fc, j hat partial x fc. So this is the second one. This is the second term. This is the second one with the negative sign. And then finally, we have a k hat partial y fx, k hat partial y fx. So this is the third term with a negative sign. So we have a negative sign here. So this is the way if we use the determinant to calculate this cross product. So you write it like I hat, j hat, k hat, and then this is the first one with the component of the first vector field or the first vector, partial x, partial y, partial z, we put it here, and then fx, fy, fz, we put it here. If you just reverse it, then you have a negative sign, which means that when we consider the cross product, the order of the operand are important, which means that if you have a cross b and then b cross a, they should have a negative sign. They should have a negative sign. For cross product, you cannot exchange it arbitrarily. Okay, so this is the way when you try to use the determinant to calculate this cross product, or actually you can try to also distribute. Then you will see I cross I will be 0, and then I cross j will be 1. So this term will have a 1 there, and then I cross k will be negative 1. So you can see, just say for this term, you try to distribute. Then you can see we have partial x I hat cross fx I hat, and then partial x I hat cross fy j hat, and then partial x I hat cross fz k hat. Okay, so this one I hat cross I hat will be 0, and then this one I cross j will become k, and then I cross k will become a negative j hat. So you can see partial x fy k hat here, partial x fy k hat with a positive sign, and then here partial x fz negative j, partial x fz with a negative sign times j hat. Okay, so I don't go through all the 9 terms, so you can feel free to use either of the method to come up with the cross product. Okay, so this is the definition of the curl, and we can see the physical interpretation for the curl is like the rotation. So here we have an example, f to be y I hat minus xj hat. To really plot out this figure, you can see, just say in the middle point is 0, 0, which means that you plug in 0, 0, it becomes a 0 vector. So in the middle we don't have anything. And then just say, for example, at this point. For example, at this point is 4, 4. This point is 4, 4. So we try to plug in 4, 4 here, which becomes 4i minus 4j. 4i minus 4j. 4i minus 4j. 4i is pointing to the right side, minus 4j pointing downward. So it becomes pointing to the bottom right. Okay, and then for example, for this point is negative 4, 4. So when we try to plug in this point here, y is 4, so it becomes 4, this point, 4i, x is negative 4, so it becomes plus 4j. Okay, so plus 4i pointing to the right side, and then plus 4j pointing to the top, so it points to the top right. And actually you can, if you have interest, you can try to go through different points to see whether it is correct, but actually it should be correct. Okay, so if you have sufficient patience to go through the whole plane, then you can see that actually the vector field of yi minus xj is like this. Okay, so the arrow not only correspond to the direction, but also related to the magnitude. If the magnitude is large, the arrow is larger. If the arrow is small, is even tiny, then which means that the magnitude at that point, the magnitude of the vector field at that point is small. So you can just seeing the you can just by seeing the arrow here, you can imagine it's like rotating clockwise. Okay, so if we try to calculate the curl of this vector field, you just plug in this one here, and then you try to calculate everything. Then actually the curl of f of this vector field is negative 2k hat. Negative 2k hat. Negative 2k hat means okay, so this is right side is the x-axis. This is I hat, and then this is j hat. I hat, j hat. So k hat is pointing out of the page. K hat is pointing out of the page. If it is negative 2k, f negative 2k hat, which means that curl of f is pointing into the page. Curl of f is pointing into the page. Maybe I use another curve. Curl of f is pointing into the page. Curl of f is pointing into the page. Okay. So actually it actually follows the right hand rule, because if you use a thumb pointing into the page, a forefinger will be something like rotating clockwise. So yeah, so this is the direction of the rotation. It follows the right hand rule, which means that actually this is the rotational axis. This axis is pointing into the page, and then the field is rotating around this rotational axis. So it is clockwise and along the negative z-axis. And actually this is the physical meaning of the curl. It refers to the rotation of the vector field. Okay, so having this fundamental knowledge, we can try to talk about some more mathematics. Yeah, so this is so-called the Divergence Theorem, or we can also call it the Gauss Theorem. Okay, so the Gauss Theorem or the Divergence Theorem is written like this. On the right, on the left side, suppose we have a vector field f. So the left side is the surface integral, the closed surface integral of the f dot dA. So in this case, it is similar to what we get in the Gauss Law. When we have a Gauss Law, we have a something like integration of E dot dA, or maybe we can just write it as a double integral here. So this is the left hand side of the Gauss law, equals Q enclosed over epsilon naught, something like that. So yeah, so probably it will be useful for us because the left side actually the same thing, except this is E field or B field, or here we have F as a general variable. Okay, on the right side we have, or something like this, we have a triple integral, but here we have a divergence of F, and then this triple integral is over the whole volume. So which means that suppose this surface integral is for this S for the surface. For the surface, we calculate the surface integral, and of course this is a closed surface, and V is the volume enclosed by this closed surface. So this triple integral is over the volume V. So we try to calculate. So rather than having the double integral for this F and then equal to the triple integral of F, we additionally have this divergence. We have divergence of F first, and then we try to integrate it over the whole volume, and then they turns out to be equal to each other. Okay, so the things is like, so it says actually the surface integral of a vector field over the boundary of the volume equals the volume integral of the divergence of a vector field over that volume. Okay, I don't try to go through the proof of this theorem because it is not difficult. I mean, it is not easy at all. If you're interested, you can try to search it on the web, or I'm not sure whether this link still works because I found this one 3 years ago. Maybe it still works, but I'm not sure. So it shows the proof of the Divergence Theorem and the Stock Theorem. Actually, it is like a generalization of the fundamental theorem of calculus. Generalization of the fundamental theorem of calculus. So when you learn the calculus, it tells you that the fundamental calculus is like if you have something like this, f of x dx integrate from a to b, it should be equal to fb minus fa, and then f is the antiderivative of the small f. So f is f prime of x equals f of x. So f is the antiderivative. Because when we try to learn the calculus, usually we will try to learn the derivative first, and the derivative is defined by the limit. The limit. The derivative is usually defined as the limit of h tends to 0, and then f of x plus h, and then minus f of x over h. So if you take x tends to 0, then this one is the definition of the derivative. And then when we try to talk about the definite integral, it is related to the Riemann sum. The Riemann sum. So without the fundamental theorem of the calculus, it feels like this definition and this definition is not related. But actually, after the proof of the fundamental theory of calculus, it actually tells you that this is the anti-operation or the reverse operation of each other. So yeah, then it makes the calculus make sense. And actually, this is the generalization of the fundamental theorem of calculus in 2 dimension and 3 dimension. So it's like we have a double integral here. We have a triple integral here. But this one, the divergence is like a first derivative, because you can see for the divergence it's actually like a first derivative. So in this sense, it is like you have a double integral, you have a triple integral, but this triple integral, one of it can be cancelled with this first derivative. Although this is not really a first derivative, but somehow similar to a first derivative with a divergence operation. Okay, so actually this is the divergence theorem we will need to use for deriving the differential form of the Maxwell equation. And yeah, maybe one physical interpretation for this one is like, just now I mentioned that if we have gradient of f is like when you consider a point, we determine how many of f is flowing out, from a point. So when we try to calculate the gradient of f over the volume, just say for this point and this point are adjacent to each other, then for this point it also related to how many f is flowing out. But as much as it is adjacent point, you can see this one and this one will just point to the opposite side, and they will cancel each other. So it feels like that all the gradient of f will cancel each other within the volume, and the only things that remain will be on the surface. So it tends to be like all these things will cancel each other except the one on the surface. So the physical interpretation is like all the inside stuff is cancel each other, and then the remaining stuff is the surface integral of f dot dA. The surface integral of f dot dA, because for the surface, yeah, no one is cancelled. For example, for this point, if you point this way, then there is no adjacent point to cancel with this one. So it feels like yeah, only the surface of the f can remain, and it turns out to be the flux of the f over this Gaussian surface or the closed surface, and then this is the divergence, and then you take the triple integral over the volume. Feel hard to understand, but yeah. But if you want to take a look at the proof, you can try this link, or yeah, if it don't work, you can try to find the Divergence Theorem or the Stock Theorem. Okay, so the next one is called the Stock Theorem. Before we talk about this one, we can just talk about a story related to it. Actually, Stock is at that time Stock is a professor, and then yeah, he had to make an exam, and one of the students called Maxwell take the exam. And then at that time, of course, no one know what is Stock's theorem, only Stock himself know. And then he make this proof of the Stock theorem as one of the questions in the exam. And at that time, only one student can really prove that one, which is Maxwell. So, and finally, Maxwell used this theorem to really to unify the Maxwell equation. Because when you try to consider the Maxwell equation, none of the equation called the Maxwell's law. At least maybe for chapter 32, when we talk about the displacement current, you know, one of the part is called the Maxwell's law, but not a complete law called the Maxwell's law. The job of Maxwell only try to unify all the Maxwell equation together, and actually the point is that we really need the Maxwell equation to solve a different kind of equation. Of course, there are some other equation or some other laws or some other theorem are quite important, just like the B-Osaka law or something other else. But with the Maxwell equation are the necessarily independent equation to solve for different EM structure. Okay, so maybe let us stop here today, and we will continue next week.